So right now, you know how to find the length of a curve using calculus, using integration, right? So we know how to find the length of something. You know how to find the volume of solid creating by either revolving in an area around a line, or if you do volume of cross sections, right? Both of those use integration. So if we're thinking about this in terms of geometry terms, right? Arc length is kind of like perimeter. We know how to find the area between two curves with integration. We now know how to find volume. The last thing that you might be finding in a geometry class is surface area, and you can find surface area as well using integration. So we can use integration to find the surface area of a solid that's created by rotating a curve around an axis of revolution. And you might be wondering why I have Doug from Up sitting on my screen. And that's because if you look at Doug, he's wearing a cone, the cone of shame. But that cone, right, is a really good visual of we're finding surface area. So when we're finding surface area of a solid of revolution, just like Doug's cone, right, there's two open circles on both ends. We're not going to be including those circles in our surface area calculation. So what we're really finding is lateral surface area. So the surface area of the sides. So basically in this case, it's like how much plastic is wrapped around Doug's head. We just want to know that area of the plastic sheet, right? And it's really thin, so it's a really good idea for surface area, so it's only a two-dimensional thing, not a three-dimensional thing. So if we think about finding surface area, Doug has this, it's called a frustumon because it's a cone that's been like lobbed off on the top. But if we think about just finding the lateral surface area of a cone, so that just means the surface area, not including the circle at the base. That's equal to pi times r times what we call L. So let's see if I can draw a good cone here. So what we're really saying is we're not going to include the top. So let me actually draw it like this, right? So we're going to have an open top, so we're not including that. So the lateral surface area is just saying we're just finding the surface area of the actual cone. So you can think of it like an ice cream cone too, right? There's an open circle at the top. So we would have our radius, and then this L is the lateral length. That was a weird cursive L. It's the lateral length. It's basically the hypotenuse, right, of that big right triangle that's sitting on the inside. So if we want to generalize this to stuff that is not a straight line, right, finding the lateral length for a cone is pretty easy because you just use Pythagorean theorem. But if I think about drawing a different kind of curve here, come on, iPad, use the straight line. Thank you. Right, so say I have, we'll do this weird curve. We'll see if I can duplicate this. Right, so say I revolve this around the y-axis. I'm gonna do my best to mirror. Right, I would get this. It's close enough. It's close enough. It's fine. There we go. It's a little better. Right, I would get this solid. Right, and I would now want to find the surface area of this. So I'm no longer revolving a straight line to get a curve, like a cone, but we can think of that lateral length as being the same thing as arc length, right? So this is really like rotating the arc length around, and I'm going to call that S, just because arc length is typically used with a lowercase s. So we can generalize this into an integral. So not going through like a formal proof or anything about how we're getting this. This is really going to turn into, for surface area, we're always going to get pi times the integral from a to b of r of x, I'm going to just label it as a function, times the arc length. So that was 1 plus the derivative of x, f of x squared dx, right? And you can also do this with a dy. It depends on what you're revolving around. Right, we can write it out twice like that, right? We can also do r of y times the arc length in terms of y, so f prime of y all squared dy. Depends on what you're revolving around. Like right now, like the way I have my picture drawn, I would need a dy integral because I'm rotating around the y-axis, right? And r of y and r of x is just the distance from the axis of revolution to the curve. Right, so all we're really doing is kind of it's kind of like combining the volume and arc length stuff together. So we have the pi, which we're familiar with from our volume integrals. And instead of having a radius squared, right, we just have the radius because we're not going up to a three-dimensional unit. And then we're going to multiply by the arc length. So we're going to do a couple of these together just to kind of show how it works. We'll do the first one without a calculator. So we're going to find the surface area of the solid formed by revolving the graph of y equaling x cubed from 0 to 1 about the x-axis. So say I draw a little curve here. Right, so 0 to 1. Right, we know that it kind of looks like this. So if I revolve it around the x-axis, right, we're going to get an open circle here on the end. Forgive my poor drawing skills, right? So we get this little surface that's going on, trying to get a little 3D here. There we go. It looks a little bit three-dimensional. There we go. Not an artist. Okay, so we know how to find the arc length, so we're going to find our derivative first. So that's going to be 3x squared. I'm going to need that to set up the arc length stuff, and then we need our axis of revolution. So our axis of revolution here, our radius of revolution, I should say, right, is this right here. So that's going to be our r, right, because that's just the distance between the axis of revolution and the curve. So the distance between the axis of revolution and our curve in this point is the function, right? It's equal to the y coordinate, and I know y is equal to x cubed. So when I go to set up my surface area integral, I'm going to have pi times the integral from 0 to 1 of my x cubed times my arc length square root, so 1 plus 3x squared all squared dx. And now it's just time to integrate. So we got pi from 0 to 1. My hand is like all shaky today. X cubed. And I've got 1 plus 9x to the 4th dx. Okay, so now we've got to think about all of our integration techniques and how we're going to accomplish this. So if I look at this, right, I have 1 degree higher in here than I do on the outside, which kind of clues into me that I'm going to use a u substitution, that could work here. So I'm going to have 1 plus 9x fourth to be my u. So if I take the derivative of both sides, I get that du is 36x cubed. Well, I have x cubed and I have a dx. I have x cubed dx left in mind, so if I divide both sides by 36, I get x cubed dx. And I'm someone who always likes to change my limits of integration for these definite integrals just because it makes life so much easier because you don't have to split up. Put it back into x's, I mean. So if x is 0, u would be 1. And if x is 1, that's 1 plus 9, that's going to be 10. Okay, so we got u is 10 there. So my surface area integral is going to turn into pi times the integral from 1 to 10, right? And my x cubed dx is going to turn into a 1/36 du. And then I'm going to have u raised to the 1/2 power in here. Okay, so I'm going to have pi over 36 as my constant out front. And then if I integrate u to the 1/2, I get u to the 3/2 times the reciprocal of that power. And then we're evaluating from 1 to 10. Okay, so the 2 and 36 is going to reduce to 1 and 18. 18 times 3 is, let's see, 30 and 24, so 54. So I get pi over 54 times 10 to the 3/2 power minus 1 to the 3/2 power, which is 1. Okay, so 10 cubed is 1,000, and then the square root of 1,000, if we just go off to the side, right, that's 100 times 10, so this is 10 root 10. So if I wanted to fully simplify this, I might leave it as pi over 54 times 10 square root of 10 all minus 1. It's going to be as simplified as I leave it today. And then let's do another one. So we're only going to do one more, and this one we can use a calculator on. So a lot of these just become difficult to integrate by hand at some point. So we're going to find the surface area of the solid, same graph. We're going to do 0 to 1 again, but now all we're going to do is revolve it around the y-axis. So slightly different graph. All right, so I got my 1s. Okay. And then if we go like this, right? We're going to revolve it around the y-axis. So my graph probably isn't perfect, but we're going to go with it. I get a nice little three-dimensional solid going on here. It looks more like a parabola than a cubic, but right, at that scale, they're kind of the same. So let's see. Now we're revolving around the dy, right? So if I want to think about my radius here, my radius is equal to my x-coordinate. So that's something to think about. And then my arc length, we're revolving from 0 to 1. So I want to change this into y's. So let's see. Let's make this is the cube root of y is equal to x, which means that my radius is equal to the cube root of y. And then if I take my my x prime now, right, because we're going to be in terms of that's y to the 1/3, so I get 1/3 times y to the negative 2/3 power. So my surface area integral is going to turn into pi, then 0 to 1 of the cube root of y times the square root of 1 plus 1/3 y to the negative 2/3 squared dy. Okay, so then all we're going to do is we're going to go to our handy dandy calculators, do second pi, right? We got math 9 for our integral, going 0 to 1, and then I've got, let's see, we're going to use the 1/3 power there for my y to the 1/3 times the square root of 1 plus, I'm going to put a fraction in there with alpha y equals, I got 1 over 3, and then my variable raised to the negative 2/3 power, I'm going to square that, move outside of my square root. Okay, let my calculator think. That should give us. Calculator's still thinking. It's a bigger calculation for it to do, so it's going to take some time. Oh boy, we're still going. So I'm just going to fill this in with some blank time. Oh, there we go. Okay, I got 2.960. There we go.